So take that same code, change the amount of cosmological constant with the same initial conditions, and here's roughly our universe. Actually, it's 0 cosmological constant, just for some fun. Here's 10 times larger in terms of energy density. Here's 100 times larger. And what we were looking for is the fact that you just blow the universe to smithereens over here. The universe expands too fast for structure to form. We were looking for various reasons where observers might end up over here, which got me thinking about where observers might end up in our cosmological simulations. On a smaller scale, the people have studied the habitable zone around stars. Hopefully you're familiar with something like this, depending on how far away from the star you are and the temperature of that star. Be in the green region if you would like liquid water on your planet. This is the habitable zone, the circumstellar habitable zone. What people have also asked is, where is the galactic habitable zone? So here now is a paper from Lineweaver, Fenner, and Gibson from a number of years ago. As a function of where you are in the galaxy, the Milky Way, and how long ago it was, where would you expect life to turn up? So out here, for example, your 2 metal pole, there's probably not many stars and not many planets out here. If you're in too close here, things are too dense, and so there'll be too many supernova going off, and it's probably a bad idea to stand too close to one of those. What we wanted to do is, because we've got a simulation of the universe, is to try to think about, can we do this sort of thing for all the galaxies in the universe? Well, at least in our simulated universe. So I now don't have a timer on me, so let me keep one eye on things there. So what is it going to depend on? We're thinking about life around stars. So we need to know where the stars form in the universe, what sort of environments they form in. Here's an example of, as a function of redshift. This is actually from data. This is Baruzzi. What's the star formation rate? So pop yourself out to redshift of 4, pop yourself in a, say, 10 to the 12 solar mass halo, and you've probably got a star formation rate of about 1 star per year, 1 solar mass per year. Notice they all sort of overlap down here. So as you get to lower redshift towards the present day, the larger galaxies, the efficiency drops. We can handle that in our simulations. One of the other things that we can think about is, what fraction of the stars that are formed are still on the main sequence as a function of time? Now, we calculated this for the previous model because we were working off into the future in another universe in those models. We did this on a time scale which is much longer than our universe. So this goes up to 2,000 billion years, which is the largest time I'll put on a plot. So that's new for me. But what fraction of stars are still on the main sequence as a function of time? That's coming out of models. What else can we look at? Well, here's one of the assumptions that Lineweaver et al. Put into their paper in that galactic habitable zone you just saw, which was 2 things: the probability of a certain planet harboring an Earth-like planet as a function of metallicity. Now, it's on quite old data, and if anyone's an exoplanet expert and wants to talk to me about how to do better than this, please do. And this one is the probability of a hot Jupiter. And again, I'm not an exoplanet guy, but here's the idea. If you're in a solar system with a hot Jupiters are very close to their stars, but they're almost certainly not born there, which means they started further out and migrated in. You don't want that, because Jupiter just wandering its way towards the sun in our solar system is probably a bad idea. On top of that, one of the things that we could get a handle on in the simulations, which was done to some extent previously, is on sort of cosmic catastrophes. Don't stand too close to any of the following things: core collapse supernova, type 1a supernova, gamma ray bursts, other stars wandering past, or your friendly neighborhood quasar. We can get a handle on these because we know the cosmic environments within our simulations. This is what took me off to a whole bunch of other literature, which is not my field, which is what happens when something nearby, like a GRB, hits Earth. Well, right? And there's a bunch of calculations back as far as the 90s here, saying, okay, if there was a fluence, which is an energy absorbed per unit area of 3 times 10 to the 8 ergs per centimeter squared, in stupid astronomy units, which is equivalent to 10 to the 4 megatons of TNT, that would essentially destroy the ozone layer for years and might occur every few 100 million years. So if we get hit by something nearby, the first real catastrophe is our ozone layer goes. Now, there's all sorts of simulations about how quickly it comes back. Turns out it only takes a couple of years, but in the meantime, the Earth's surface has been irradiated by UV radiation from the sun. The top layer of everything small in the ocean dies, and then everything that eats that dies, and we're in a bit of trouble. The reason they calculated this is to try to understand whether any of the mass extinctions that have happened over the history of Earth, this is biodiversity as a function of time. This comes from paleontology, and we're way outside my area of expertise now. Every now and then it sort of takes a dip. These are the mass extinctions. So, that one killed the dinosaurs. Can we understand any of these in terms of what say, a gamma ray burst hitting Earth might do? However, if we're looking for the habitable zone in general, what you'll notice here is that life sort of bounces back in a couple of maybe tens of millions of years. And, we're probably here because that happened, maybe. I don't know. Watch Jurassic Park again. What we want is a real disaster that really sort of knocks planets out entirely. So there are a number of papers which have tried to calculate that. Forbes and Loeb in 2018 calculated how much fluence does it take to completely remove the Earth's oceans. And there's the number for you, 10 to the 18.8, which is an enormous number in terms of fluence. But there it is. You can make that calculation. You can do this for fun yourself. It's a back of the envelope kind of thing. How much to take off the Earth's atmosphere? A bit less. How much to take off Mars's atmosphere? What they work out is that these sorts of fluences on this scale, how close to a black hole do you need to be before these sorts of numbers come into play? And actually, if you have a 10 to the 9 solar mass black hole, which is, we've seen those, we're talking kiloparsec scales, which is rather large, right? On a tenth of a kiloparsec scale, you can wipe out the Earth's atmosphere. You just literally unhinge it. It's gone. It's off. It's out into space. Another paper by David Sloan calculates that if you have a fluence more like 10 to the 15, you boil the entire Earth's oceans. That's enough energy there. Again, go to your favorite textbook on thermodynamics and do that calculation yourself. So what we can do is take limits on the fluence and turn that into, okay, if a typical core collapse supernova gives you 10 to the 51 ergs, and if anyone knows where that number comes from, please tell me. I tried to find it. Anyway, about 0.3 parsecs, which is pretty close. Obviously not a scale you can model within a cosmological simulation, but statistically you can do probabilities. Type 1a supernova, similar sorts of limits. The way we can get a handle on these, similar to gamma ray bursts, except they're beamed, so they can hit you at a larger distance. The way we model these in the simulation is for gamma ray bursts and core collapse supernova, they're dependent on the star formation rate. 2 minutes. Wow. Good luck, everybody. One of the other things we can work out is how often do stars wander past, right? And that's it. So if you shoot a star at the solar system and you want to unhinge the Earth, make its orbit at least very not round, and you're throwing something at 1,000 kilometers an hour and it's a star, how big is the solar system you've got to hit? Well, it's a 10th of an AU. That's sort of the aim you need. So there's all the things we did. What we can calculate, I'll just jump ahead to this one, is the amount of habitable time. So here's the idea. Send out your drones, your minions, on every star that forms in the universe with a little stopwatch. And if a planet forms that looks like it might be suitable for life, have them start their watch. If an extinction event just killed everything on the planet, have them reset the watch to 0, but then start it again, because that planet might make life a second time. But for extreme events where you say take off the entire ocean, just have your minion stop the clock, set it to 0, and that's it. If you then add up all those times, you're getting something like the number you would multiply by the probability of life forming on a planet, which we don't know because the biologists haven't told us yet. And you will get something like how much life there might be in the universe. So that's what this plot does for you. So say it's 10 billion years after the Big Bang, and you're in a 10 to the 12 mass halo, as we are, 1 times 10 to the 12, something up there. For every solar mass of baryons in that halo, the universe is making something like 1/10 of a gigayear worth of habitable time. So the other thing you can calculate with this, and I'm running out of time, so I'll jump ahead, is what kills you. So all those processes that might wipe you out, what's the probabilities? So what's the rate at which a typical star planet system in a given universe as a function of time might be wiped out by an explosion, GRB, or a supernova? Well, early on in the universe where things are dense and there's lots of stars nearby, you're in trouble. But late in the universe, things are actually pretty nice. So quickly on the future, that was a function of mass. I'd also like to do it as a function of radius, working on that. The effect of quasars I haven't mentioned, but we can look into that in more details. The things I'm really interested in, which I'm not quite sure about, is should I be worrying about cosmic rays, although their propagation's a real theoretical challenge. M dwarfs, someone tell me about whether they're too flary for stars, and I should buy some real estate at Andromeda, because 10 to the 12, it's pretty actually nice. So the Milky Way is pretty good as well. All right, thanks very much.
Hi, interesting talk. I've seen a few talks on this, so I don't get figures. Have you seen the work of Brian Fields? He and his collaborators have quite a few papers on looking at how supernova affect.
Oh yes, yeah.
So life and habitability. So I expect, yeah, if you haven't read some of his papers, I suggest you have. He's looked in this in some detail.
Yeah. By the time you're back at what can I put into a cosmological simulation model, all of that detail gets a bit blurry, and all I really need is like sort of a blast radius. You know, how close do you have to be? But yeah, that sort of modeling, I've been trying to read all of that as well.
Yeah, kind of on a similar. I was just wondering, because when you had your core collapse type 1A gamma ray burst, you only had gamma ray burst dependent on metallicity. Like they're, as far as I'm aware, all dependent on metallicity. So is that incorporated into it, or is that too much detail to?
Okay. Let's talk later. Again, outside my field. The star formation rate depends on metallicity, and then if all I'm doing is taking the star formation rate, the initial mass function, which I assume is independent of metallicity, which probably isn't. Yeah, bingo. And then cutting off anything bigger than 10 to the 8 blows up. So if there's metallicity dependence there, then I can improve my model.